Okay, let us start today's class of Vlsi lab. From now on, we are working with the digital experiments. In case of analog experiments, it was simulation and then layout. Now, in the case of digital experiments, the procedure is slightly different. Now, before dealing with the actual procedures of digital experiment, let me tell you some basics about how are we going to conduct the digital experiments in Cadence. Now, when you switch on into the system, you will have to log in and then right click and open terminal, because we are going to work with the Linux platform. Right now in the lab, we have this Red Hat Enterprise Linux platform. As you already know, Linux is a very stable, virus-free environment. Windows is prone to a lot of virus-related or other operating system-related bugs, whereas Linux is a freeware, and Linux has got many GUI interfaces such as Red Hat, Ubuntu, and so on. So it is very safe to work with the Linux. Even if virus comes into the system also, the virus will be marked as a file and it will remain like that. It will not get executed there in the operating system. So we are going to work with Linux, and when you open terminal, you will have to get into the C shell by typing the command csh. In Linux, you have both GUI as well as command interface. It is easy to work with commands only that way. So as such, Linux operating system has got many shells. As you already know, any operating system has got kernel at the center, around which we will have shell, around which we will have command interpreter. That means the interface between the user and the system is by means of a command interpreter. Later on, we will have a shell, and shell will have a connection to the kernel. Kernel will have connection with the hardware as such. So in Linux, there can be many shells. Any expert programmers can design their own shells. There are many shells. One shell is C shell. One more shell is Bourne shell, named after the scientist Bourne himself. We are going to work with the C shell. That is why you have to give the command csh for getting into the C shell. Now, after you get into the C shell, we have already kept one script file in the system which can easily enable the execution of the Cadence software itself. Otherwise, it becomes very difficult to keep on typing the Cadence related commands in the Linux environment. So we have kept all those commands in a batch file called cshrc, C shell run command. That is the expansion for that particular file. It is basically a shell script. So it is saved in these folders or directories. In Windows, we call it as folders. In Linux, we call it as directories. It is like an inverted root structure. Inverted tree structure, I should say. Which means, in a tree, initially you will have roots, then you will have stem, then you will have branches, then you have leaves. In the same way, in the computer system, we will have root directory or home directory, after which we will have different other directories or branches. Finally, we will have files. Files are like leaves here. So, source home / install / cshrc. So, the cshrc is present. From the home directory, there is another directory called install, and there this file is present. And when we give this particular command source, the contents of that cshrc are going to be executed by the operating system. Now, this is the basic procedure when we start working with Linux. Let us proceed further. Now, you will have to enter your design. Now, our design is in digital format. We are going to use Verilog. So before that, you will have to create your own design directory. For example, it can be design 1, or you can give any other name. by using a command called mkdir, make directory, and you can give the name for your directory such as design1. Now in this design1, you can write the Verilog program of your design. For example, we have given the name here at codefile1.v inside this directory. In the sense, just like in Windows we have MS Word, here in Linux we have one editor called gedit, graphical editor. Using gedit, you can write your Verilog program and then you can save it in the directory called design1 or any other name which you have given. Similarly, you can write the test bench program for the same design. For example, codefile1_tb.v is the name example we are giving. You can save this test bench program in the same design1 directory. Now you have two design files or two Verilog files, I should say. One is your regular design file, one is the test bench file. This you can type the program using gedit. Gedit itself is a command there. Let me show you that. Then later on, let me come back. Okay. Now today's experiment is write the switch level Verilog code, verify using test bench Cmos inverter, 2 input Cmos NAND and NOR gates, 2 input XOR gate using Cmos logic, 2 into XOR gate using path transistor logic. Now the theory part you already know. Still, there are some instances. Let me read it. The transistor level modeling is referred to modeling hardware structures using transistor models with analog input and output signal values. At this level, the hardware component is described at the transistor level, but transistors only exhibit digital behavior and their input and output signal values are only limited to digital values. At the switch level, transistors behave as on-off switches. Verilog uses 4-value logic value system. So Verilog switch input and output signals can take any of the 4 values, that is 0, 1, Z and X. 0 is logic 0, 1 is logic 1, Z is high impedance and X is unknown. That means X can be having 0 or 1, but Z is neither 1 nor 0. As you remember the CMOS inverter, if NMOS is on, it is sinking current. At that time PMOS is off. If PMOS is on, then it is sourcing current. At that time NMOS is off. But neither NMOS and PMOS are on, let us say. That means, let us say the input is at the middle of VDD. Imagine. Or else, let us say input should be given 0, then PMOS is on. Input should be given 1, then NMOS is on. Let us say input itself is not properly following the specs. In that case, output can be neither sourcing nor sinking. Or let us say a situation arises where input is at exactly VDD by 2 and both PMOS and NMOS are working in the saturation region. They are working like two high value resistors, imagine. In that case, there will be enough drop across PMOS also, enough drop across NMOS also, and the output also will be VDD by 2. In that case, output will not be following the 0 and 1 specifications. It may be exactly in the middle. That is also called high impedance. Now, X means it can be 0 or 1, but it is unknown until the signal computation is complete. So, in Verilog, the signals can have these 4 values. Please remember, we are working in the digital description of the design. So, we will have to specifically define our noise margin for our designs. So, Verilog can have 0, 1, Z and X. Now, we can define this inverter circuitry by means of 2 transistors, one NMOS, one PMOS. Let me write the circuit here briefly. Now this is our regular inverter. Upper one PMOS, lower one NMOS. Now let me change the color. We already know that the upper one for PMOS is source, lower one is drain, and NMOS upper one is drain, lower one is source, and this is gate. Inputs are gates. Now in the digital domain, how do we define? We have to write a code for this switch level description. In the gate level description, it is really very easy to write code for an inverter. You have already worked on it in the 4th semester HDL lab, where you used to write program simply as input x and output y and assign y is equal to not of x. That was very easy in the gate level description of the design. Now, how do we write a code for this inverter now? For that, you can see we are having an NMOS as a command. This is basically a primitive command, we can say. In Verilog, switch level description is possible. We can simply write NMOS N1 out data control. Now, control is the input. Control is the input to the gate. Out data control. Now, let us see later on what is this out data control. NMOS N1 out data control, PMOS P1 out data control. That NMOS is the name of an instantiation. N1 is an instance, which means you already know this process of instantiation. We have a primitive called NMOS. That primitive can be instantiated any number of times, N1, N2, N3, N4 like that. Let us say we want to have 100 NMOSFETs in our design, we can have N1 till N100. So that middle N1 is the instance name. NMOS itself is the instance. Now this NMOS has got 3 terminals, right? Gate, drain and source. So here output is at the drain and input is at the gate and source is at the ground. Accordingly, we can give in our design, we can give the names. You can see here it is D and this is drain now. Out is drain now. And data is in now. And control is source now. That can be the syntax for this NMOS command. Similarly, for PMOS, it can be out data control. Now, control can be VDD and VSS. It is different for both the MOSFETs. Whereas gate is the input, drain is the output. That way, this particular command NMOS or PMOS, they have their own syntax and it has to be followed in the same way. Okay, let me stop annotating. So that is instantiating an NMOS switch, instantiating a PMOS switch. Okay, in this way we can write now, see. Now this is the main design module inverter.v, where we have a compiler directive called tick timescale 1 nanosecond, 1 nanosecond. This tick command, you can see this tick here. You can see a small symbol called a tick. This tick timescale is a compiler directive. In the sense, we are telling the compiler that our timescale is having 1 nanosecond divisions and the minimum resolution is 1 nanosecond. That means if there are fractions, they can be rounded off to 1 nanosecond and we deal with the 1 nanosecond unit. That is the direction which we are giving to the compiler. That is called compiler directive. Next, we can write the code for the inverter, module inverter out comma in. Out is the output, in is the input. Output out, input in. Now you can see supply 1 power. Supply 1 is already defined in the library, in the cadence library. Now to supply 1, we give the name power, and to supply 0, we give the name ground for our convenience. Now we can instantiate the PMOS and NMOS switches. You can see PMOS out, power in, NMOS out, ground in. So let me write the circuit diagram once again. I'm crudely writing. because I am using the mouse only here. As long as the purpose is served, it is enough. So now output is out, input is in. Let me change the color. I am not showing the body contact here at all. In analog design, we used to specifically write the body contacts, but in digital, we will not write the body contact, because the reason is we will only define the design by means of the Verilog code. Later on, the tool knows when there is a process called synthesis, where the Verilog code is going to be converted into the hardware. There the tool knows about the NVL and PVL, P sub and all those things. So we don't have to worry too much about that substrate connection in the digital domain. But it is very much required in the analog domain, because analog domain is basically a full custom design. Full custom design in the sense, right from the transistor level, everything we do. Whereas in the digital domain, we cannot say that it is a full custom design. It can be a semi-custom design, where an inverter's complete description along with the layout can be available with the tool, and we can simply write a Verilog code to connect all those gates. Now they are all called standard cells. An inverter, all the logic gates, even flip-flops, even adders, they can all be saved, or they are available as standard cells inside the Cadence library. Whenever a Verilog description is required, those standard cells can be picked out and they can be connected. That's all. So that way in the digital domain, we are writing code only. We are not going to go for a full custom design. That is called standard cell based design. To some extent, we can say that it is semi-custom design, because somebody has already done the complete description, functional as well as physical description of some basic electronic designs, which is available in the library. That is the idea. So now, in the tool, it is called as supply 1. Now we will call it as power. For our convenience, we will call it as power. And in the tool, it is called as supply 0. We will call it as ground. Now for supply 1, by default, 1.8 volts is assigned in the tool. And for supply 0, 0 volts is assigned in the tool. Those are the nomenclature of the Cadence tool itself. We are using power and ground for our sake, that's all. So output is out, input is in, which we already know. Now we have to write this PMOS out, power, in. You can see PMOS and then out, power, in. That means this is now source, this is now drain. Again, here it is drain, here it is source. Which means you can see the syntax here. Out is drain, power is source, and in is gate. So the syntax of this PMOS is drain, source, gate. You will have to remember this. I told you earlier that there is a syntax for this particular primitive. So PMOS is the primitive, its syntax is drain, source, gate. Similarly for NMOS also the syntax is drain, source, gate only. You can map it to this. Drain is output, source is ground, and gate is input. That way you remember this, it is DSG, drain, source, gate, always with the switch level description of the transistors. So this is how we write a code for an inverter in the digital domain. It's a simple code, but still we have purposefully included this in the syllabus so that you will understand how a switch level description also can be done in Verilog. In the HDL lab in 4th semester, you did only a gate level description, which was quite simple. Here we are writing the switch level description. Now you may wonder why switch level description is necessary in digital domain when the inverter is available as a standard cell. Yes, inverter is available as a standard cell for a given technology. Maybe for 180 nanometer, maybe for 90 nanometer, maybe for 45 nanometer. Let us say when you start working with the new technology, you will have to design standard cells, right? Someone has to design anyhow standard cells. How do they design standard cells there? For designing standard cells for a newer technology, we can have a switch level description. That is the idea. Because PMOS and NMOS are already defined in the Cadence library as primitives, and then we use this syntax to define PMOS and NMOS. Now you can see that just with this command, we have connected gate to gate and drain to drain. You can see here. Let me change the color. Now gate to gate is connected here and drain to drain is connected here. You can see this. PMOS out, NMOS also out. It is the same terminal, which means we simply wrote two lines. But the way in which we have assigned those variables or names, variable names. When we give out and out here, it is syntax is drain there. So drain and drain of PMOS and NMOS are connected just by these two lines. Similarly, in, gate, gate, it is both are in only. So gate are connected. Whereas the source of PMOS is connected to power and the source of NMOS is connected to ground. So this is the switch level description of the inverter. Okay. I hope this is understood. If there are any questions, you can ask me now, or else I'll proceed with the discussion of the test bench. Are there any questions? Okay, there are no questions. Let me proceed. Now please remember, this is the switch level description of inverter. Now let us see the test bench. Now this is the test bench module. We can name it as inverter underscore test.v and you can save it in your directory. Again, the first line is tick time scale 1 nanosecond / 1 nanosecond, the resolution and the minimum duration. This is a compiler directive. Now module inv underscore test. Here you can see this module inverter is containing a sensitivity list where we have out, in. Whereas in this test bench, there is no sensitivity list. Can you tell me why? Can anybody tell me this module inverter underscore test is not having a sensitivity list, whereas this module inverter is having out, in defined because they are the two output and input variables utilized. So can anybody tell me in the test bench why we do not have a sensitivity list? Let me write a small diagram here. Yeah. Kuldeep has given the answer, only we are defining input, sir. Yes. It is we who are defining input and output both. So let me simply write one small thing here. This looks like a bench. I'm purposely writing something like a bench. Let me change the color. So I have written a bench, which I call it as a test bench now. Now you can see below the bench, there is this DUT, design under test. Now the test bench itself is going to give the stimuli to the design under test. And the test bench itself is going to take out the response from the design, which means that input signal will have 4 levels, 0, 1, x, z. All the 4 levels can be specified in the test bench here. So that is called stimuli. And the response of the design, that is output. Output also can be again 0, 1, x and z, depending upon the way in which the signals are processed inside the design under test. Test bench itself will collect the responses, and later on the responses which are collected from the test bench can be plotted on the screen by means of another tool. We will see the tool later on. In Cadence we have many tools. Earlier you have used Virtuoso. In Virtuoso you have used tools called Spectre and Ashura. For physical verification we had used Ashura, and for functional verification or simulation we had used Spectre. Along with that we had Virtuoso layout editor, we had a Virtuoso schematic editor. We had already used 5 tools there in Virtuoso. Similarly, in digital domain also, we will have the tools now. Right now, I am telling only about writing the Verilog code. Later on, when we start compiling, I will tell you the names of the tools at that time. So, test bench is also a Verilog code. Design under test is also a Verilog code. Now, we will have to test the design using the test bench code. Test bench code will have the stimuli. Test bench itself will collect the responses, and those responses can be plotted on the screen by means of a software tool. So for this matter, module inverter underscore test is not having any sensitivity list, in the sense this test bench will not be connected to the external world at all. The test bench resides within the computer system, and we are not going to connect any physical input to our code, neither we are going to take any physical outputs from the code. Everything is going to be handled through the test bench itself. That is why test bench will never have the sensitivity list, because the test bench is not connected to the external world. Then what is going to be connected to the external world? Once you verify this design, Verilog design, and after the design is synthesized, after the synthesis, when the hardware is available, that hardware will be manufactured in the foundry. And after the hardware gets manufactured in the foundry, later on it is going to be connected to the external world. Otherwise, the design which we are right now verifying is not going to be connected to the external world. That is why test bench will not have the sensitivity list. Fine. I hope this is understood now. Let me proceed. You can see further, output is called as wire, input is called as register. The reason is, just like I showed you the picture here, output can change anytime, whereas input is stored with the values 0, 1, x, z, the way in which we have test bench input waveforms, the way in which we define the stimuli inside the test bench. That is why inputs here are called as input here, only one, because we are working with inverter. Only one input that is defined as register or declared as register, and output is declared as wire, because output is going to be computed from the design itself. Now instantiate the inverter module. See, we have written a code called inverter. I will show you the code here. Module inverter is the code. Now we can call this inverter here. That is called instantiation now. Just like we had instantiated Nmos and Pmos, here in the test bench we are instantiating the complete inverter using the word inverter itself, because that is the name we have given. We have only one inverter now, so we can simply give the inverter's instance name as I1, because right now we are testing only one inverter. Inverter I1 and out comma in, that is the sensitivity list and the port declaration. Now in the test bench, let us apply stimulus. or stimuli, so to say. We have this initial, then we have this begin. I hope you recall whatever you learned in the HDL course in the last semester. You must be remembering the difference between initial and always. Now, as such, Verilog is concurrent. All HDLs are basically concurrent. In the sense, when we write all these lines in the code, the lines will not follow a particular sequence. It is concurrent, means at once the execution is going to happen. But whenever we give the statement such as always or initial, we are making the concurrent execution as a sequential execution now. You already know that all the combinational logic are concurrent. In the sense, when you write a code for a combinational logic, you don't have to use the wordings like initial or always. For that matter, when we wrote the code for inverter there, we did not use always there, because inverter is basically a concurrent execution as such. I hope you recall all those terminologies which you studied in the fourth semester. If at all you still have doubts, you can ask me later on if you want more clarification in this semester. Otherwise, I presume that you will remember all those basics. So, Verilog itself is concurrent, and in test bench, it cannot be a concurrent execution now. Why? Because in test bench, we give one value 0, then one more value 1, then one more value x, one more value z. When we give it this way, one by one we will have to give. That's why you can see initial is the word given here. This is telling the simulator that from now on the sequential execution will start. Till now it was concurrent execution. From now on the sequential execution will start. I was always giving this analogy of Ravana and Kumbhakarna in my theory classes when I used to teach HDL. Now Ravana has 10 heads. We can give 10 plate meals to him at once, and he can consume all those 10 plate meals. That means we can say Ravana is having a concurrent execution. On the other hand, Kumbhakarna also has got the ability to eat 10 plate meals, but we will have to give him one after the other because he has got only one head. So that way, for Kumbhakarna, we will have to say that you follow the sequential execution. For Ravana, we can say that you follow the concurrent execution. Now, Verilog is a combination of Ravana and Kumbhakarna. Till now, we were having Ravana. Now, in test bench, we are having Kumbhakarna. Means, one after the other, we are going to give 0, 1, x, and z. Because test bench can handle only one input value at a time. Test bench can never be concurrent. The design module can be concurrent because design module is connected to a combinational logic. But if it is a flip-flop or a counter, that also has to be sequential there. Otherwise, all combinational logic, they are concurrent. Now we are testing a combinational logic by giving multiple signals. So it has to be sequential one after the other. That is the reason why we give this initial. When we give this initial, the execution happens only once here. If at all we give always, the execution enters into a never-ending loop. That's the difference between initial and always. So initial begin input is equal to one quote. There is a single quote. You remember this, tick is different and single quote is different. That tick or back tick was utilized as a compiler directive, whereas you can see a single quote here or apostrophe. This indicates one position, binary bit, and value is 0. Then #10 indicates 10 nanoseconds delay. We have already given the unit as a nanosecond there in the beginning when we gave the compiler directive. So in is equal to 1 apostrophe B0 semicolon #10 semicolon. So after 10 nanoseconds, the input will have the value 1. Then after 10 nanoseconds, it will have the value x. Then after 10 nanoseconds, it will have the value z. In this way, we are giving 4 values here. And that's all. Then we have the end module, that is the end of the test bench. So if at all I have to write it like this, input will be initially 0, after 10 nanoseconds it will be 1, after 10 nanoseconds it can be x, after 10 nanoseconds it can be z. Now this x, we don't know whether it is 0 or 1. Z, you can see it is somewhere in between 0 and 1. So this is now 0, this is now 1, this is now x, this is now z. So in this way, we are giving these 4 input values. Each duration is 10 nanosecond. So naturally, this has to be sequential, isn't it? Because it is one after the other. It has to be sequential. That is why this initial word is required. Where we tell Ravana that from now on, we do not have 10 plates meals at a time. We are going to give you 1 plate meal, 1 at a time. Because we have only 1 cook in our kitchen and he is having only 2 hands. That is how we have to tell to Ravana also. Even the Verilog is very much powerful. Whenever it comes to sequential description, we will have to follow the sequence only one after the other. Test bench has to be always of a sequential execution because we are giving input values one after the other. So any questions here? If you have any questions, you can ask me or else I will proceed. Okay, as there are no questions, let me proceed further. This is the writing of the Verilog code for design as well as the test bench. Now we will have to simulate it. Now there is a tool called SimVision tool. Now before this is the simulation snapshot. Okay. Now before this, let me show you the process of compilation. Let me discuss now these procedures. So write the Verilog test bench program for your design inside design1 directory. Now the design entry using HDL gets finished. That's what I showed you till now. Let us say the steps for simulation now. Initially, both of your Verilog programs have to be compiled using the command ncvlog file name -message. ncvlog. Native compiler Verilog. Now there is a native compiler within Cadence tool. That compiler can be used. Just like when you worked with the C language, you might have used the Turbo C or Quick C for compilation. Here, as Cadence is already having digital as well as analog designs, it can have its own compiler. That is called native compiler. NC is native compiler, Vlog is Verilog. We are telling to the tool that ncvlog. Please understand now, we are in the terminal, in the Linux terminal, and we are giving the command which is part of Cadence. Because we have invoked that CSHRC. Okay. So, ncvlog, you can give your file name along with an extension. .v is for Verilog, .vhd is for VHDL. And -mess, actually it is messages. You need not type the complete messages. If you give the first 4 alphabets, that is enough. The tool will understand it. So this -messages is we are giving that if there are error messages, it should be displayed on the screen. Otherwise, Linux is not that user friendly. In the sense, Linux will not give messages unnecessarily unless something goes wrong. Because there is a saving of resources here. As resources are scarce and as the Cadence requires a large amount of memory, what Linux does is it will use always minimized resources. Just like in the IT company, they say cost cutting. Now during this pandemic period, they are cutting cost like anything. For anything and everything, they are reducing the cost now. For that matter, they are saving money to the company as such because survival is now the biggest problem with the industry as well during this pandemic time. So in the same way, as Linux is a very efficient operating system, it will utilize minimum amount of resources. Unnecessarily, it will not add anything that way. So if this hyphen mess is not given, then the messages will not be shown at all. That is why we want to know whether compilation happened properly or not. For that, we give this hyphen mess. Now you compile this ncvlog, first design file, then the test bench file. You can see now why we gave the underscore here, because that hyphen is meant as a Linux command there in the terminal, in the cadence atmosphere. That is why we are differentiating by using this underscore in our file name. Now, during compilation, if there are any errors, you will have to correct it there. Generally, if you have any typo errors, it will show it there, and all the typo errors, you will have to correct it. They are generally called syntax errors. If there are logic errors during compilation, it will not be known at all. Okay. So after compilation, you have to elaborate the top module. You remember the picture I wrote about the test bench and the design under test. We call the test bench as the top module because test bench is at the top. Design under test is at the bottom. That's why I wrote that picture in that way only. So after compilation, basically compilation is what? Compilation is checking of the syntax errors. Now you will have to elaborate the top module. Top module means test bench. Inside the test bench, we have instantiated our inverter design. Please remember or recall the test bench code. Inside the test bench, we had instantiated the design module also or the main module also. So if you elaborate the top module, that is enough. What is elaboration? You can see here. The process of elaboration builds up the instances and then connects them. Right now in our today's example, we have only one instance. But in general, a digital design can have thousands of instances, lakhs of instances, crores of instances, right? One microprocessor chip or a microcontroller chip can contain millions of transistors, billions of transistors. So there can be hundreds and thousands and lakhs of instances there. It need not be one inverter inside a microcontroller or a microprocessor chip. There can be thousands or lakhs. Even other logic gates also can be thousands and lakhs. All of them will have multiple instances. So the process of elaboration builds up all those instances and then connects them. It has to connect them with each other. The way in which we write the code, all the instances have to be connected together so that signal has to be applied to the whole circuitry and the verification can be done. That process is called as elaboration. Now this process of elaboration was not there with your other programming languages such as C language or Java. Why? Because they are not hardware description languages. They can be called as software description languages, where there is only going to be compilation and simulation. Here we have three steps called compilation, elaboration, and then simulation. Now the process of elaboration builds up the instances and then connects them. Care must be taken that you elaborate only the top module, namely the test bench. Because in the test bench itself, the main design modules are defined, right? Or instantiated, right? So the attribute for the command should be the test bench module name. You can see here, NCELab. Native compiler, elaborate. You need not fully type elaborate as such because as I told you, the first 4 characters are sufficient for the tool. NCELAB, NC elaborate, module name of the test bench. You can see the test bench module name. Whenever you do this module name, in elaboration, we will not use the file name. You can see here we have used the file name. But here we are using the module name. Remember this, during elaboration, we will not be using the file name. We will be using the module name. That too, the module name of the test bench only because we are elaborating test bench itself or the top module itself. So NCELAB module name -access plus RWC. R stands for reading, W stands for writing, C stands for compiling. RWC. We are giving the access rights to the elaborator tool. Please remember, compilation tool is different. NC-Vlog is also a tool that way. NC-ELAB is also a tool that way. NC-SIM later on is also a tool that way. Or they are all part of the tools. Let me write the name of the tool. The name of the tool which we are using in this digital domain is called Incisive. INCISIVE. But the tool is not shown anywhere right now here, because all these commands, NC-Vlog, NC-ELAB, NC-SIM, these three commands are part of this tool called Incisive. As I told you, Cadence has got many software tools within. We are invoking the tool by giving that particular command. That's all. So, NC-Vlog is for compilation, NC-ELAB is for elaboration, NC-SIM is for simulation. All three are part of this tool called Incisive. Okay. So, to the tool, we have to give the access rights. Tool must be able to read, tool must be able to write, tool must be able to compile. Those are the three basic operations. You may say, sir, compilation is already done now, right? But compilation is done only for our Verilog files. Afterwards, when the top module is being elaborated, internally again all those Verilog files, it will have its own methodology to connect all those instances. So there also read, write, compile rights have to be given to the elaborator tool. Without elaboration, we cannot simulate any digital design in Cadence or in any other software tool also. We have company like Cadence, Synopsys, Mentor Graphics, Magma. We have many such companies. These are all called EDA companies, electronic design automation companies. Now all these companies will have their own tool packages, software tool packages. They will have different names for their own tools. We are using Cadence tool as such. So, the elaboration is a very important process. After elaboration only, simulation is possible, because during elaboration only, instances are built up and they are connected. That means the circuit diagram is internally connected. Now, later on, next step is to simulate the design using the command NC-SIM. You can see NC-Vlog, NC-ELAB and NC-SIM. NC-Simulate. Here even if you give the first three characters, that is sufficient, because even if you give SIMU also it will work that way. But SIM is sufficient because there are no other commands which are having this SIM there. So native compiler simulate, module name. Which module name? Module name of the test bench itself now, because we have elaborated the test bench or top module and we are simulating the test bench only as such, because in the test bench only we have specified the stimuli or the values for the input. So here also the simulation has to be performed using the test bench module name. When GUI is used, the sim vision tool will be invoked and the waveforms can be seen. If you simply give NC-SIM module name, then the tool will not plot it as such. It will simply simulate, and the simulated output has to be seen again by means of using some other command or specifically giving those commands. Now, the tool has got one more thing called -GUI. If you give this -GUI, there is another cool tool called Sim Vision that is going to plot these values and is going to show you the output. As I showed you earlier, in analog designs, we had Virtuoso schematic editor, then we had a Spectre simulation. Spectre was the tool which had one ADE, analog design environment, where we used to specify transient analysis, AC analysis, DC analysis. and the tool used to plot the graph. Here in digital domain, there is nothing called transient AC-DC. It is basically transient only here. We will not be seeing any DC and AC analysis here because this is purely digital. So we can say here it is a transient analysis. That also we did not mention it here. We simply say simulation. When we simulate, if at all we use this -GUI as the continuation of the command, then automatically SimVision tool will be invoked and waveforms can be seen on the screen. So we have a tool called Incisive. Along with Incisive, we have one more tool called SimVision, which will plot the output response of our digital design. So let me show you the SimVision tool now, before discussing synthesis. Now let me discuss the SimVision tool. After invoking the SimVision tool with the command ncsim module name -GUI, two windows will be opened. One is the SimVision console and the other is the design browser window of the tool as shown in the snapshot. You can see design browser 1, SimVision. You can see here simulator and you can see inverter_test. This is the one. This is the top module's name which we had given inv_test. So you will have two windows here. One is the console, one is the design browser. You can see the console below. Now, as the next step, you need to click on the module name on the left side of the design browser window. You will have to click on this module name inv_test. You can see a small plus here. Small plus you can see. Let me zoom in. Yeah, now you can see the small plus. That plus is an expansion. When you click on this inv_test, it will show all those instances now. That plus is an expansion. Anyway, let me zoom out. So, once you click on the module name on the left side of the design browser window, as soon as you click, you will see all the port names displayed in the right of the design browser window. You can see it here now. Let me zoom in. Once you click, you will see this in and out. You can actually expand this and you can see there also. Or when you click it, actually we have to tell the simulator tool that which one we want to plot. That is the idea here. So once you click on this, you will see this in and out, which we have defined. Now after that, select all of them. You will have to select both of them. You can simply give Ctrl+A also, or you can click on one and press this Control key on the keyboard and click on the other one also. Right now we have only two variables to be plotted. Let us say in some bigger digital designs, you don't want to see all the intermediate values. You only want to see the initial and the final values. That way you can select particular variables. Here, as we have only two variables, we are selecting both of them. That is the selection, in and out. After you select, now click on the waveform icon on the right hand side corner. You have a waveform icon here. You can see this waveform icon. This is that waveform icon. This is for plotting. Right now you can see the value as recorded is X and X because TestBench has not yet given the values to these variables. Now when you click on this waveform icon, let me go down. When you click on the waveform icon, later on you can click on the play button. You can see the play button in the design browser. Let me zoom out to show you the play button. Okay, in this snapshots, that play button is not shown. Yeah, here you have, right? Here at the left corner, you have this play button. I hope you can see this here. Yes. You have this play here. Just like in our DVD player, we have this play, pause, and this is revert back, all those buttons are there. You can explore all these buttons later on. We will not be using these buttons in general. We are going to use only this play button. Once you click on this play button, the tool, SimVision tool, is going to plot. Let me zoom out again. So, click on the waveform icon on the right hand side corner of the design browser window. I have shown you the waveform icon here. Now, click the play button on the waveform window to run the simulation. The waveforms will be generated as shown. Now, you can see the waveforms here. These are the waveforms. You can see, initially we gave 0. Let me zoom. You can see this in and out. And initially we gave input 0. You can see the output 1. Then after 10 nanoseconds, we had given the command #10 there. After 10 nanoseconds, we give the input 1. Output is now 0. Okay. Now, later on, after 10 nanoseconds, we have given the value x. X is unknown. You can see this red rectangle here, which means it is neither 0 nor 1. It may be 0, it may be 1. We don't know. So that is this x. For input x, output is also x. Okay. Now lastly we gave z. Z is neither 0 nor 1. You can see it is in between. It is VDD by 2. It is neither sinking nor sourcing that way. Then when it is z, output is also x. Can any of you tell me, when input is 0, output is 1. When input is 1, output is 0. When input is x, output is x. Because input is unknown, it may be 0 or 1. Output can be 1 or 0. Again, that is unknown. But when input is z, why output is x? Can anybody tell me? When input is z, output also has to be z, no? Why output is x? Can anybody tell me? No answer? Previous value is the output. No. Input will not have, inverter will not have memory, right? Inverter is a combinational circuit. It will not have any memory. So there is no storage of the previous value. That is not the exact answer. Think again. Any other answer? Okay, the answer is, we are defining input as Z. Z is exactly VDD by 2. In our case, the supply voltage is 1.8. That means Z is at 0.9. But now, output may not be exactly at 0.9, right? We are going to define noise margins. Let me write this. Oh, it came so beautifully now. Let it be. Now this is 0 volts and this is 1.8 volts. In general, let me change the color now. In general, now this is 0.9 volts. This is now 0.9, which is exactly the barrier or the demarcation between logic 1 and logic 0. But point is, if it is above 0.9, will the circuit to be taken it as 1 or 0? If it is below 0.9, should it be taken as 0? Ideally, we want 0 and 1.8, right? But practically, let me write a line. Practically, signal can be somewhere here also, and signal can be somewhere here also. When practically when the signal is in between 0.10 and 0, at what value we should take it as 0, at what value we should take it as 1? Who has to make the decision now? As designers, we only have to make a decision. That is where we have to define something called noise margin, NMH and NML. Noise margin for high, noise margin for low. For example, we can define, let us say from 0 till 0.5 volts as logic 0. From input signal 0 volts till 0.5 volts or 500 millivolts, we can consider it as logic 0. Above 500 millivolts, we will say it may be noise. It may not be a valid signal to be taken as logic 0. Now, I am just giving a crude example of 0 to 0.5. So 500 millivolts is the margin which we are defining. Similarly, here if it is 1.8 for high, if it is 1.8, 1.8 minus 0.5 is 1.3. Now 1.3 till 1.8, again there is a 500 millivolts margin. Below 1.3, we will say it cannot be taken as a valid value. We will say it may be noise there. It may be a stray change over there. Circuit is not behaving properly as per logic. In all digital logics, it has to be 0 or 1, right? Unlike in analog. In analog, we can have infinite number of values in between. But in digital, we should have two distinct values. So we have to define this noise margin in this manner. Okay. It is we designers, based on our own system specifications or system requirements, we will have to define our noise margin. And if we define the noise margin in this way, now what about between 0.5 and 1.3? Between 0.5 and 1.3, still it can be 0, still it can be 1, we don't know. But how do we define? Now the point here is, for the tool, when input given is 0.9, output cannot be exactly 0.9 also, right? Output need not be at 0.9, because transistor to transistor there can be differences again, right? In analog, we are taking care of even small, minute characteristic changes. But in digital, we are not bothered that way. In digital, we are not bothered about characteristic changes to be taken care of, because we want two distinct levels. So, in such a case, tool has not yet completed the synthesis. Hardware is not yet available. Tool will not bother much. Or the writer of the tool also will not bother much. He will say if the input is Z, output can be 0, output can be 1. I don't know. It can be, if input is 0.9, output need not be 0.9 in the case of our inverter. It can be slightly above 0.9, slightly below 0.9, depending upon the behavior of those standard cells, right? Right now, inside the tool, they are all now standard cells. They are not full custom designs. In analog, it is full custom design, where we design the MOSFETs, we design the inverter, we design everything there using the layers. Whereas in digital, they are all standard cells. Using standard cell, we are going to simulate. So, even a MOSFET is also a standard cell here now. It is characterized for this given technology. So, the tool will not bother about whether output has to be Z. Output can be X. Output need not be VDD by 2. Output can be above or below, depending upon the transient behavior of the switches. That is the answer. So with this, let me stop today's class. If you have any questions, you can ask me. Or else I'll stop today's class, but meeting will be on. Write your observation book and post it in the Google class. Today Deepak has not yet joined to the class. I don't know whether he has created the assignment in the Google class or not. Let me find out later on. But let me stop recording now. Let me go into a mute mode. If you have any questions, you can ask me. Otherwise, I'll stop sharing the screen now. As far as synthesis is concerned, as it is a much bigger topic, let me discuss it in the next class. Okay. As there are no questions, let me stop recording. Let me stop sharing.